Okay, so good afternoon, everybody. So today we're going to just continue our discussion on Monday about the U statistics. So just as a quick recap, we first defined a statistical functional just as a generalization of our parameter of interest. So we write theta as T, which is the functional of a CDF representing a distribution. So this is something we want to estimate. And sometimes we call this our estimand. So to estimate this, maybe more specifically, we define the expectation functional. So if it's called expectation functional, which is a special type of T, then it will have a special form. So it can be written as the expectation of some function g with arguments y1 to ym. And here for the expectation, we write the subscript f to represent the distribution. What it means is that y1 to ym are IID following this distribution f. This is what we mean by this notation. Okay, so you see that when n equals to 1, it's the simple case. We just have one argument, right? When m equals to when m is greater than 1, we can have more complicated forms. So let me just tell you one example to let you see under what case we can have m greater than 1. So obviously, when we have g as the identity function, and then n equals to 1, then this expectation functional is reduced to the population mean, the mean of f, right? So if g y is just y when m equals 1, right? Under this special case, then tf is basically expectation of y that follows f. So it's the mean parameter. But under what case can we have m greater than 1? Let's think about this interesting case. Okay, let's look at an example where this g function, actually this g function has a name. It can be called a kernel function. But we know we have kernel functions in other cases, like in machine learning, right? We have the kernel-based method. So here, don't confuse those two kernels. But mathematically, they have some relevance. So like in here, in the m equals to 2 case, this g function, if I define it to be just y1 minus y2 squared over 2. And recall that in our last lecture, we said that even though this g function may not be asymmetric about its m arguments, we could always create a g star function that is symmetric, and the g star function and g will give the same expectation functional. So because of that, we say we can assume g to be symmetric without loss of generality. And that's exactly the case here. Here, g is specified to be symmetric between y1 and y2. So with this g function, let's think about its corresponding expectation functional. Let's write TF. Okay, by definition, it's the expectation f under f of g y1, y2 that follows f IID. So if I just take this form of g into the expectation and expand it, I would have 1/2 times the expectation of y1 squared plus y2 squared minus 2 times y1, y2, just to open up the square form. And then because of the IID, y1 and y2 are IID, you see expectation of y1 squared will equal to expectation of y2 squared. So I can cancel one copy. I just write expectation of y squared. Y represents y1 or y2. And here for the interaction term, the 2 and 1/2 will cancel. So I keep the minus sign. but then expectation of y1 times y2, because of independence, it becomes expectation of y squared. Again, here the y is a general notation for random variable that follows f. You see, what is this? Square expectation of square minus square of expectation. That's the definition of variance, right? This is exactly definition of variance of y that follows f. So therefore, you see, this g function, using it as an expectation functional, we obtained the variance parameter of distribution f. So you see, this is a one way to see why we would need this g to be multidimensional in some cases if you want to describe some more complicated parameter, more complicated than the mean. Okay, so that's the expectation functional. It has its input as a CDF and it will output a scalar value, or actually it could be a vector value. Here's just the example we have here is scalar value. And then the next question is how to estimate this theta, this statistical functional. And the most naive estimate is by plugging in. So that's what we call the V statistic from the last name von Mises. So this V statistic denoted by Vm is defined as the same expectation functional applied to the empirical CDF, f and hat. That's what we have. And then therefore, you see, what does this imply is that I could just have, I would just write expectation under f and hat of g at y1 to yn. So then y1 to yn would be IID from this empirical CDF. And by definition, they would take values. So let's say f and hat is defined by a random sample x1 to xn that come from f. Then what it means is that it will have probability mass 1 over n at each of the x1 to xn. So therefore, you are going to draw y1 to yn from that discrete distribution with n values. So last time we talked about this, and we say that the issue with this definition is that it's possible some of my yi's could be the same xi, could be the same value. So that will actually cause this Vn to be biased in that case, okay? But if n is equal to 1, we don't have this concern because we just have one y here, and that y each time can only be drawn from x1 to xn, so we won't have that issue there. But when you have multiple arguments in G, whenever you have y1 to yn, some of them happen to be the same random variable here of x1 to xn among them, then you will have some issue here. So therefore, to correct the bias, we propose the UN, unbiased estimator. U stands for unbiased. So that will remove the possible repetitive elements of sampling y1 to yn from x1 to xn. So in the definition of UN, we need to consider how many possibilities can we have unique y1 to yn. That would be to sample from n items to draw m items, right? So that possibility is n choose m. And with that, we also consider these things when they are sampled. So we consider just one order because of the symmetry of G. Otherwise, so for example, y1, so if y1, y2, just two of them, if they happen to be x1, x2, or x2, x1, we consider them to be the same. So without worrying about the order, we just set those m arguments to be ordered by the original index from the smallest to the largest. So here, in the m summation, I require my I1 to be bounded below by 1 and less than IM. I don't allow equal sign here because they cannot be from the same x, less or equal than m. Okay, with this, then I denote the random sample as xi1 to xim. So they would be the values of y1 to yn here because they are sampled from x1 to xm. Okay, this is the definition of the U statistic. And now let's coming back to this example with this specific G, what it is. So in this example, m equals to 2. So I first write m as 2, and then I have a double sum, right? So basically I have I less or equal than I1 less than I2 less or equal than n. Then this G becomes GXI1, XI2. Okay, then let's consider what possibilities we have here. So that's by definition. Now we want to simplify this a little bit. So we could actually consider I'm having I1 less than I2, but if I want to make it simpler, or because this term here is basically this n choose 2 inverse is just 2 times n minus 1. That's it. And then in this sum, I have I1 less than I2, right? So to simplify this term, if I multiply this I1 less than I2 by 2, I could change this less than to be unequal, and the 2 can be gone. So I will have 1 over n times n minus 1, and this sum becomes I1 doesn't equal I2, GXI1, XI2, okay? So I have that. And furthermore, I can even make the sum simpler. Let's just imagine, what if I1 equal to I2? Then based on this special definition of G function, the G function will be equal to 0. So adding those back will not change my sum value. So therefore, I can further write it as I1 from 1 to n, I2 from 1 to n, GXI1, XI2. Because in the equal cases, I have G function equal to 0. Okay, so now you see, I'm able to do something simpler. So with this G defined in this way, I will be able to further expand the form as 2 here, xi1 squared plus xi2 squared minus xi2 times xi1, xi2. Okay, I have this. Then based on the same argument as how I do the combination here, because of the IID, now here is xi1 and xi2, they are IID. Yeah, right. And also another thing is that basically the summation, or actually I should take it back here. IID is not useful, it's just algebra. So here, when we take the sum, let I1 goes from 1 to n, sum of xi1 squared, and the sum of I2 go from 1 to n, sum of xi2 squared. The two sums are equal. It's just whether I denote the index by I1 or by I2, but that doesn't make a difference. Okay, so therefore, we should be able to show that if you just do the play with this summation. So let me just write it down. So basically, what I'm saying is that if you take the sum of I1 here, okay? So if you take the sum of I1, then basically I2 is just times n. So basically, because there's no I2 involved, so you're just having that n times the sum of xi1 squared. So then that n and this n can be canceled, and you're going to have a 2 left here. So what I'm saying is that you would have 2 times n minus 1, okay, times the I1 go from 1 to n, xi1 squared. That's what you have for the first term. You can remove one sum. And for the second one, you can similarly remove one sum and be left with I2 go from 1 to n, xi2 squared. Okay. And finally, the cross term must be left, but 2 and 2 can be canceled. So you have minus I1, I2, xi1, xi2. So we have this. Okay, so finally, we can actually show that if we simplify this form, what can we do? Consider just this double sum. First, I will use the fact that the summation of xi2 can be written as n times the sample average xn bar, okay? And you know this xn bar has nothing to do with xi1. So when I'm left with xi1 like this, I can actually have this term out. So what I'm saying is that let's first write it as I1, xi1, sum I2, xi2, right? So by this relationship, I can write it as I1, xi1 times n xn bar. And this has nothing to do with I1, so I can get it out. And sum of xi1 itself is another n times xn bar. So therefore, you see, I will have this equal to n times xn bar squared. That's the key. Okay, so this term is now simplified. And for this term, I can combine them into one term because the summation is the same no matter if I use I1 or I2 for the index. So together, you see, I'm going to have n minus 1. So now I just reduce the sum index as I from 1 to n, xi squared. I combine these two terms. And for here, you know, I can have this n squared and can go get me one n to cancel with this m. So therefore, I'm left with minus n minus 1 n times xn bar squared. Okay, finally, I can combine these two terms into just n minus 1 sum I from 1 to n xi minus xn bar squared. So I'll leave this last step verification for yourself. But you see, basically this U statistic just happens to be the unbiased estimator for sample variance we learned before. So this is just one case to show that why U statistic is considered more general, because what we learned before, a lot of the unbiased statistics we learned, estimator we learned before can be written as special cases for the U statistic, as long as you specify the expectation functional in the correct form. Okay. So now we see this as a special case. Hopefully this can make the understanding easier. So the question we want to address for today's lecture is to derive the asymptotics for U statistics. How do we do that? So coming back to the general form, this is the U statistic. So the question for today's lecture is, what's its asymptotic distribution? Okay, that's our question. So first of all, for its asymptotic mean, it should be obvious because we already know it's unbiased, right? So the first thing we know is that the expectation of UN, again, I'm carrying this F with me, okay, to denote the distribution is denoted by F. This is known to be just TF, the parameter of our interest, the expectation functional. So that's why we know this is its mean. Okay, and we would denote it. So just for today's lecture, to be consistent with the notes, we denote it as theta. Theta is the thing we use here, the parameter. So that's the mean of my U statistic expectation. And it's the finite sample mean for any finite n. So it's also the asymptotic mean. So the next thing we will try to do is to derive its variance. Okay, what's the variance of the U statistic? Actually, for this, we are going to introduce a method to actually do this calculation. And this method, which we will show very soon, is called the H projection method, stands from the name of a very famous statistician, Houghton. So that H comes from his last name. So here, let me just give you this result, which we call as a theorem. So this theorem is about this question. So it states if your m is small, that means if your n is greater than 2m minus 1, which actually would make sense because we have this m as fixed if we define the functional, the expectation functional, right? So this g will have only a finite number of arguments. But this n is our sample size, x1 to xn. And by asymptotics, we're letting the n go to infinity. So that's why we can easily have this hold. So under this condition, this theorem says the variance of um under f will take this interesting form, okay? 1 over n choose m. Let k go from 1 to m. Let m choose k. Let n minus m choose m minus k times something we call sigma squared. Okay, so this is the thing we are going to introduce by the Houghton's method, H projection method. But let's first look at this form. You know, before I say what this is, you should have some intuition if you're familiar with combinatorics. So what we're saying here in this form is very like what we call the hypergeometric distribution. That means you choose m from n, and then among the m, you choose k to be something as one part, I should say. So among the n, k is one part, m minus k is another part. Okay, so basically you can think of this as we are doing the overlap, and here each set has m elements and the two sets overlap by k elements. So when you are drawing a distribution like this, you are going to have a form like this. So essentially, this is related to our definition of sigma k. Okay, so now let's define what is the H projection. Which is very interesting, actually. It's defined as a conditional expectation. So recall that we have this expectation functional right here as the expectation of g, y1 to ym. So here the expectation is taken for all the random variables y1 to ym. But what if we don't take the full expectation, but just the conditional expectation? That's it. So here we define a function gk, okay, as with k arguments. So let's just write as y1 to yk. And it's defined as the expectation, still I write f, of the g function with the first k arguments fixed as y1 to yk, and only the remaining n minus k arguments are random. So yk plus 1 to ym. So in other words, I have m minus k random variables here, okay? And the first k arguments are fixed. So what does this definition mean? Essentially, it means that we are doing the expectation conditioning on big y1 equals small y1, big yk equals to small yk. So that's why we say it's a conditional expectation. So therefore, this is writing y1 and yk as the, as the fixed values. What if we allow them to be random? Then you can easily see that if I write them as random y1 to yk, correspondingly, these things are fixed So we should say that it's the conditional expectation of G, Y1 to YK plus 1 to YM, conditional on Y1 to YK. Okay, so this is the definition of this GK Y1 to YK. And we are conditional on the first K argument. So therefore, as a result, the conditional expectation itself will be a function of what it is conditional on. So Y1 to YK. So that's what we get out here. Okay. So this definition, this new function GK, is defined based on G, and itself has a very nice property. That is, if I take expectation of GK at Y1 to YK, what would happen? We know by the simple tower rule, right? We have double expectation. Take conditional first, then the outer expectation is for the random variable in the condition. We would actually restore the full expectation. So therefore, this is equal to expectation of G, Y1 to Ym, okay? And that's my theta. So in other words, the key is that this thing also has expectation equal to theta. But what's the benefit of doing this? So we would show that this will give us a nice way to express this variance of UN, the unbiased, the U statistic, in terms of this sigma K. So actually, this sigma K is defined exactly as the variance of GK at Y1 to YK. Okay, this is how we define the sigma K square. So you can imagine if I do G1, what does G1 mean? G1 means that I'm just conditioning on the first one random variable, the rest are being taken over by expectation. So therefore, that will be the only random variable that's left there is Y1, and that will be sigma K squared. So with this definition, okay, we can show that essentially we can write the UN's variance just by enumerating Y1, or sigma 1 squared, sigma 2 squared, up to sigma M squared. But why is that beneficial? The immediate reason is that for this term, if you expand it, you can easily see that. Let me go here. So if all the sigma 1, so let's say sigma 1 squared to sigma M squared, if they are all bounded, okay, finite. So with this inside, so if you open up these numbers, n factorial divided by n factorial divided by n minus n factorial, so n will be here, n will be here. And if you cancel the relevant terms, you can actually show that the first term would be just of the order m squared times sigma 1 squared times big O 1 over m. So it's on the order of 1 over n. It's going down to 0. And for the remaining terms, you can show that they are of the order 1 over n squared. So they go down to 0 faster than the first term. In other words, asymptotically, the variance of UN is dominated by this term. So that means you only need to care about the variance of G1, Y1. That's the thing you want to care, you only need to care about. So that can simplify the form of our, or it can simplify the asymptotic variance form. And also this form, this variance is going down to 0 at the rate of 1 over n, also tells us a very important message. That is to describe the asymptotic distribution. To get a stable, non-degenerate asymptotic distribution for UN, we need to multiply it with a divergent constant. And that divergent constant should be root n. So that root n, once enters the variance being squared, becomes n, can be canceled with this 1 over n. So these are the messages we learned from deriving this variance. Okay, does that make sense? Okay, so with this, then basically we have a rough idea about what the asymptotic variance or asymptotic distribution should be like. So here, what we have here is the intuition that we will derive the asymptotic variance of root n times um minus the theta, its expectation, it converges in law to what? That's the question we want to answer. And also we roughly know the asymptotic, so we should know the mean. Okay, the mean is 0 because of unbiasedness, and the variance with the stabilization, it will be m times sigma 1 squared. So we have these two already. This is the asymptotic mean, this is the asymptotic variance. But what's the distribution shape? Is it normal? So that's the remaining question. How do we show the asymptotic normality? So we are quite close to what we need. And also for this theorem, right? We didn't prove it, but I think for probably, I can quickly say it, but the proof is actually quite simple. So what you need to do is basically to open up this as the sum right here. So when we take the variance of we're basically taking the variance of the sum. And inside the sum, we are going to have the variance of each term and the covariance of different terms, right? So therefore, if you think about it, here we make sure that for each set of I1 to IM are unique. So in our sum, but even though they're unique, they may share some elements. So we consider their overlap to be one element, right? That would mean they have some covariance there, right? And that covariance needs to be calculated. And at the most term, they can share the m-1 components, right? So these are the possible covariance cases we consider. And that will actually correspond to here. So I consider K to be 2G terms, how many arguments they share. And I can let K go from 1 up to m-1, as I said. But what if it's n? When it's n, it means that I'm calculating the variance of G xi1 to xim. So because the variance of itself is actually equal to the covariance of itself and itself, right? So that gives me the m. So together, you see, basically to show that I just need to show one thing, that is the covariance of, to prove this theorem, let me change to a different paper. So to prove this theorem, the key is to show that sigma k squared is equal to the covariance of 2G functions inside my definition of U statistic right here. I need to show that the sigma squared is equal to, say, G. I think I'll use the Y notation to be simpler. Y1 to YK, YK plus 1 to YK, YM. Okay, this is one term. And the other term is G Y1 to YK. The same as here, they share those Y1 to YK, but the remaining are different. YM plus 1 to YM plus M minus K, because I need M minus K random variables here. So, you know, these things and these things are different, but these and these are the same. So as long as I can show this, then the theorem would automatically hold because of the definition of variance. Just open up that summation in the U statistic. Okay, but how do I show it's actually the covariance? what I'm going to do is just to simply use the definition of covariance. Okay, so just for simplicity, or not definition, the covariance, the property, the covariance is equal to expectation of the product minus the product of their expectation. So I'm going to use that, but just for notation simplicity, I think I'm just going to write it as, okay, expectation as G. I think I'm just going to write it as Y1 to K or Y1 to M, just for simplicity as this, because otherwise too long, times G, Y1 to M, and M to M plus 1, sorry, M plus 1 to M plus M minus K. Okay. This is the expectation of the product minus the product of expectation. So I'll write expectation G, Y1 to M times expectation G, Y, that 1 to K, and yep, M plus 1 to M plus M minus K. Okay. So for here, this is obvious, right? So I know this expectation is just my parameter theta, and also here it is also. So what I have, here is that all these random variables, they are IID from F. So that still holds. So that's why they have the same expectation. But the difference is that here they share K random variables. So I need to consider that in my calculation of this expectation of product. To make this simple, you can see why this Hofstad's projection would help. So if I'm conditional on the shared variables y1 to yk, then the expectation would be actually simple under the condition. The reason is that the remaining m minus k variables here, m minus k random variables here, they are independent. So then I can open up this product by that conditional independence. So you see what I'm saying is that what I would do is I would do the tower rule. So I would have this conditional on y1 to k, the first k random variables, and then I will get another expectation for y1 to yk. So for the inner part, I can separate it into, by conditional independence of the remaining variables, I can separate to expectation of G. Let me write it here. Expectation of G of, Y1 to M, conditional on Y1 to K, okay, times expectation of the second G, Y1 to K, M plus 1 to M plus M minus K, conditional on Y1 to K. You see, I'm just separating this product, expectation product, as product of expectations by conditional independence. And now you see, both of them are equal to my GK. They're both equal to the same thing. So it's basically GK Y1 to YK. So I'm spelling it out now. Now, write the definition of GK, just take a look. So you see in this expectation, it doesn't matter here, I have notations YK plus 1 to YM, or I have YM plus 1 to YM plus M minus K. They are just random variables. Once taking the expectation, I will still have GK Y1 to YK, what's being conditional on. So that's what I have here. So therefore, you see, this thing is squared, right? So because they're both equal to that, so the first term together, you see this term would just become the expectation of gky1 to yk square. So I should say, maybe I make it more clear, it's square here. So the square is inside the expectation. Okay, so now by definition, you see sigma k squared is defined as the variance, right? Variance of that. And I know this expectation square is always equal to variance plus the square of expectation. And here the variance is sigma k squared. Expectation of it is just theta. That's what we have here. Its expectation is theta. So it's sigma k squared plus theta squared. And now you see this is only for the first term, right? I have the minus here, which I haven't considered yet. I said it's theta times theta. So I will have minus theta from here. So together, you see, I have shown that this is just equal to sigma k squared. So sigma k squared is the covariance of these two terms. And I just need those covariances in my variance of un. So that's why I have this form, the statement in my theorem. And because of this, and because we have n here and here with simplification, I can show that the variance term is dominated by the term with in the order of 1 over n and times the m squared sigma 1 squared. So that's why in the asymptotics, I just worry about this term. So the things come together for you now. So the key is to derive the variance of U statistic, right? And we need to open it up. And to simplify our notation discussion, we introduce those covariance terms, and those covariance terms can just be defined simply as the variance of this GK function. So if you don't think the GK function makes sense, it's just an arbitrary construction. You can think about it from the perspective of deriving the variance of UN, then you will see it makes more sense just to simplify our notation. Okay. Does that make sense to everybody? Do we have a question here before we proceed? Okay, so I think if you read the notes afterwards, then you can see it was described in a different order. So we introduced things piece by piece. While here, I try to give you the higher level idea first before going to the details. So hopefully putting my lecture and the notes together, it will be easier to understand. So still back to our question, right? Our ultimate goal is to derive the asymptotic normality. But you know, speaking of this, our fundamental tool is the central limit theorem. So we always want to start from there. So how can we make this as some sum of IID? That seems to be very difficult. The reason is that if you look at this form of UN, look at this form, right? So it is a sum, but in the sum, you see for every possibility, different possibilities will share random variables. So that's why you don't have independence there. So that makes it quite difficult. Again, now we are going to use conditional expectation to help us again. So what we will do is that we are going to introduce a construction called tilde UN. Okay, this tilde UN is going to be constructed based on what we need. So it's going to be defined as the summation of I from 1 to n. Don't forget, x1 to xn is my sample, the sample we will work with. Okay, so it's defined as the expectation, and x1 to xn follows f. So I put f here of un minus theta, the thing I have here, conditional on xi. So you see, this construction will actually make it IID. So because we said by conditional expectation, maybe I should use bracket. By conditional expectation, each one of them is just a function of xi, right? So they are IID. So what I'm saying is that by this definition, EF, U minus theta conditional x1 to EF UN minus theta conditional xn, they are IID. Does this make sense to people? Yeah. So because x1 to xn are IID, right? So condition on each of them, this is a function of x1, this is a function of xn, right? They should follow the same distribution. Same transformation on x1 to xn. Okay, so with this intuition, now we can see by adding this additional layer of expectation, doing this condition expectation, we can make this tilde UN as a sum of IID so that central limit theorem applies to this tilde UN. And then what's left is that if we can derive the asymptotic distribution for tilde UN, can we associate it with the asymptotic distribution of UN, the original UN minus theta? That's our hope. So if the two things actually have the same asymptotic distribution, then we are happy. Okay, so the remaining for today will be try to address this problem. How can we show that? First, how can we derive the asymptotic distribution for U and tilde? That's the CLT. And how can we show that U and tilde and UN minus theta have the same asymptotic distribution? Okay, so first, let's try to address one question. What is this term? That means what are these n terms? Can we express it in a more explicit way? Yes, we can. So let's just try to derive it, right? Okay, so what is the EF UN minus theta conditional xi? What is this? So again, let's try to use the definition of U statistic. That's what we always start with, right? So 1 and choose n, and sum I1 less than IN, right? And of course, bounded by 1 and n. And then expectation goes inside. We have G xi1 to xim minus theta, right from here, minus theta conditioning on xi. That's what we have. Okay, so now we just need a discussion. Is xi one of my xi1 to xim? If it is, or if it is not, the result will be different. Okay, so let's just discuss those two cases. So if I happens to be one of I1 to IM, what would happen? It means that we are fixing one of the M arguments, but also varying the other M-1 arguments, right? So in this case, we are taking expectation with 1 being xi. That's exactly our definition of G1, with one argument being conditional on. And because of the symmetry of G, I can let the xi to be put in the first place. So that means I'm conditioning on the first argument being xi. So that's exactly G1 xi. M minus theta should stay here. Okay, otherwise, if I is not one of I1 to IM, then this conditioning should be gone, right? Because they're independent. So I can remove the conditioning, then it's just expectation of this G minus theta, and that will give me 0. Okay, so sorry, I should say that this specifically, these two cases is about, it's about this expectation only. I haven't talked about the sum yet. For the sum, I just need to consider for how many cases can xi be one of them xi1 to xim. For how many cases xi is not one of them? So now you can see I only need to consider the cases when xi is one of them because the other case is 0. So I don't need to care. So let's just do combinatorics again. So when xi is fixed to be one of them, how many possibilities can I have for choosing the remaining n minus 1? That should be n minus 1, choose n minus 1. Right? Out of those, n divided by the original denominator, n choose n here. When that happens, inside the sum, I would have g1 xi minus theta. That's it. And then cancel these two terms. I would keep m over n times g1 xi minus theta. Okay, so this result, I think, will make it more clear that each of these, I'm saying here IIDs, these are IIDs are basically G1 xi for this one, G1 x1 about, this is G1 xn, right? Subject to this shift and scaling, but then you can clearly see that they are IID. So in other words, let me just put it here. You can see that we have this U tilde here. So this U tilde n is just the summation. I can make it out n over n I from 1 to n G1 xi minus theta. That's it. And now everybody should be able to see that central limit theorem would apply. Okay. And then finally, it should be very easy to show that. I'm just going to quickly skip the derivation, but to quickly move to the result, that central limit theorem tells us that actually you can consider this n to be the average denominator. So therefore itself, this can be considered as an average times n, okay? So this will tell me by central limit theorem, root n times this U tilde m, and its mean is 0, so I don't need to subtract 0 here. We'll convert the law to normal distribution, mean 0, and the variance just happens to be n squared and the variance of G1 xi. Variance of G1 xi by definition is sigma 1 squared. Okay, so we're here. So what can you see from this result? This UN tilde has asymptotic distribution given by the central limit theorem. And also this term, the asymptotic variance term, m squared times sigma 1 squared, looks very much like the term I have here for the variance of UN, right? So that says if I do, so basically from here, we have, let me just write it down. We have, let me scroll up a little bit. So we have from here, so from this term right here, if I multiply by root n, okay, you can have root n un minus theta is also of the order m squared sigma squared plus the remainder are of the order 1 over n. So you see other terms are going down to 0, but this term doesn't go down to 0. And this term, sorry, I should have the variance, my bad. The variance here. Okay, variance is this, and this variance just happens to be of the same order as the asymptotic variance of this root n u tilde n. So we are one step closer to show that they have the same distribution. Okay, so what's left for us? So the thing is that, by our previous Slutsky theorem we learned before, we know that to show So it's sufficient, I should say, sufficient to show that root n times un minus theta minus u tilde n. Okay, if I can show that this thing goes down to 0 in probability, then I'm fine. So this itself would imply that I have root n un minus theta converges in law to the same asymptotic distribution here. Okay, so that will be good enough. That will be good enough for us to show this. Does that make sense? So, and then what's left is to show why this converges to 0 in probability. And to show this, our first thought, as you have done in your homework, is try to show whether we can have convergence in the square, in the mean square. So that means if we can have, or convergence of quadratic, like that. So if we can show that, so this can be applied by showing the expectation of root n of this un minus theta minus u tilde n squared. So if we can show this thing goes down to 0, then it should be good enough. Okay, and in order to show this, we can actually open this up and see what happens. So because theta is known to be the expectation of un, so we are going to use that property. And using that property, we can have this term here is basically equal to, so I'll just write it again, root n un minus theta minus u tilde n squared. Okay, this thing, if I open it up, I can show that it's equal to n. First, I let the root n be squared and get it out. I will have the variance of, and I carry f with me, variance of un. The reason is because theta is the mean of un. And also what I have here is something I need to have the cross product, right? So I should have -2 times expectation of f, and that will be what? It's un minus theta un tilde. I have this, and finally I have the expectation of un tilde squared. So I'll have 3 terms here. Okay, and then for the middle part, actually, I can show that it's one of the lemma in our lecture notes, but I guess I can skip this part by not trying to prove it because it's quite straightforward. So I can show that for the middle part, very interestingly, expectation of un minus theta times u tilde n, this term is equal to, just happen to be equal to expectation of un tilde squared. So this nice result, whose proof is in the notes, okay, you can check or you can verify it. If you want to verify it, I can just tell you, you just go back to the definition of un tilde. That's here. So this is the definition of un tilde, right? Sorry, I should say this is the definition of un tilde. We simplify it. So using this definition, you are just going to put it here, replace this by this sum, and then you are going to do the product between un minus theta with this g1xi, right? And then again, to do that, you are going to use the Taylor rule to help you. You first put the conditioning on xi. So then therefore, with the conditioning on, you can more easily work with the product of g1 xi minus theta and times un minus theta. The reason is because once you are conditioning on xi, this can be considered a constant and you can get it out of the conditional expectation. So that thing will become easier. So I'll just, and also don't forget the definition of this u tilde m is basically this, right? So therefore, if you have the conditional expectation of un minus theta, conditional xi, if you have that, then you are going to create another copy of this. So that will help you simplify this calculation. But ultimately, we can show that this is just that, okay? And then because we have -2 of this plus this, so they can be canceled. So what's left for me? So because of this, what's left for me is n times variance of un minus the expectation of un tilde squared. Okay, and then does this go down to 0? Yes, it does. The reason is, again, what we have said in the previous page, because we know this variance of un, this is equal to m squared sigma 1 squared order 1 over m, bigger 1 over m, and this is equal to m squared sigma 1 squared. Let me see. Sorry, this is okay. Give me 1 second. So, right. So sorry, I shouldn't say this. This is equal to this over n. Yeah. So n times that equals this. So because of this, then we can show that they are equal to each other and they can be canceled. And sorry, what I'm saying. So this is that, this is that, right. So don't consider this, that makes sense. So therefore, I have, so let me just write one more step. N times the variance f un minus n times expectation f u tilde n squared. Okay, so what I'm saying is that the first term is m squared sigma 1 squared plus other things of the order 1 over n, they are going down to 0. And this is just m squared sigma 1 squared. Yeah, so that's why their difference is going down to 0 as n goes to infinity. So because of this, we have shown that this thing, its squared expectation is going down to 0. So this is sufficient, stronger than saying this is going down to 0 in probability. And this itself implies that this term has the same asymptotic distribution as this term. So that's why altogether, we have derived asymptotic distribution for the U statistics. So the key here is to utilize conditional expectation. That's the key. And very interestingly, we show that even though we are basically defining, this UN tilde as a conditional expectation, as a sum of conditional expectations of UN minus theta. So the intuition is that every time we conditional on one, we are conditioning on one xi. And xi, we have n of them. So we have n terms, they are IID, we take the sum. This allows us to use central limit theorem. But very interestingly is that even though we are doing this as an approximation or projection to each xi, by the term H projection, still we are not losing in the asymptotic distribution because the difference, the other terms are going down to 0 at a faster rate than 1 over n. So that's why when we multiply by root n, the other terms will still go down to 0, but what's left, the major term, they have the same asymptotic distribution. So to me, I think this is a very interesting result. And also to derive the asymptotic variance, we just need to do that G1, the projection, and to get its variance. Okay, so let's try to see an application of this result. Going back to the example here. In this example, we show that the U statistic is the sample variance, right? So we show that UN is equal to this. And we know that in a previous lecture, if you recall, when we talk about the asymptotic distribution of sample moments, back then we showed the asymptotic distribution for sample variance. So I'll just write that result here again, just for your information. So we actually show that, let's see, recall. So in our previous lectures, at that time, I remember we called this as S squared. So if in that case, we have this UN as probably as n squared, and that's 1 over n minus 1 xi minus xn bar squared. So at that time, what we did is that we used the delta method to go from the joint central limit theorem applied to the joint distribution of the first order sample mean and the second order sample mean, right? So summation of xi squared and summation of xi and summation of xi squared. We use those two things to get us the delta method to get us the asymptotic distribution for the sample variance. And so if you recall, at that time, we can show that this will converge to the population variance sigma squared in law to normal distribution zero mean, and the asymptotic variance would be equal to, let me just write it in our current way here, variance following the F distribution of y minus u squared, the variance of the square term. That's what we have as the asymptotic variance. Okay, and now let's see whether we can use our current result to derive the same thing. Okay, so in our current result, by the U statistic theory, what we have? So here we have m equals to 2, right? So, and the asymptotic distribution just involves, sorry, I think I missed the square. It just involves m squared times sigma 1 squared. So therefore, we should expect to have un minus its parameter, still sigma squared, convergent law to normal zero mean. M is 2, so it's 4 times sigma 1 squared. What's left is to derive sigma 1 squared. And the sigma 1 squared is known to be, is defined to be the variance of G1y, okay? And what's G1y, right? G1y needs to be calculated first. So G1y is defined as the expectation, or let me just write this lowercase, expectation of G with the first argument as the lowercase y, second argument as the y2, okay? And the G function in this example is just this y squared plus y2 squared minus 2 times y times y2, okay? And let's simplify it. So lowercase y is a constant, only y2 is the random variable. Expectation of y2, we know it's equal to mu. So in our notation, here's the mean, that's the mu. Expectation of y2 squared is variance plus mu squared. So together, we are going to have this as y squared plus sigma squared plus mu squared minus 2 times y times mu, okay? So this is my G1 function. And now let's try to look at what's its variance, okay? So now putting it into the variance, sigma 1 square as variance of this with random variable y. So in other words, it will be variance f, and I put it down here. So this lowercase y becomes the random variable y squared plus sigma squared plus mu squared minus 2 times capital Y times mu. Okay, so that's it. And then you can see in the numerator, I'm having a square term, y squared plus mu squared minus 2y mu with an additional sigma square. But I know this additional sigma square shouldn't change the variance, so I can remove it, right? I can safely remove it without changing the variance. So I'm having, and this 2 comes out as 4, 1 over 4 variance of y minus mu squared. Okay, and then you see putting this into here, I obtain the same result as we had before from the delta method. So this is just an example to show that we can use the general statistic asymptotics to actually redo this work and have the same asymptotics as we have before. So does it make sense to everyone? Okay, great. So in our lecture notes, which I posted to CCLE, we have an additional section about what we call the multi-sample U-statistics. So in that case, we are dealing with a scenario where we don't have one random sample x1 to xn. Instead, we may have more than one of those, let's say S of those. So in this case, we can define a U-statistic for all the samples jointly. So then everything will be scaled up. So we will not just consider one sample, but S samples. But the techniques there are actually quite similar, except that we just make it a little more complicated. That's one extension. So from one sample to multi-sample. And another extension is to go to multivariate U-statistics. So what does that mean? So you can see that here when we say x1 to xn, we implicitly assume that they are scalar valued. But what if they are vector valued, right? So then they become random vectors. So in this case, if we define a U-statistic, here the approach is that we try to define U-statistics dimension by dimension. So let's say x1 to xn are p-dimensional, then we will here correspondingly define p-U statistics, p-U statistics in total. So one for each dimension. And in that case, you need to worry about the covariance of different dimensions. So things become more complicated. But I guess for those things, we don't need to really talk about them in this class. So I think with this, you should have the capacity to understand them if you need to use them in the future. Okay, so before I conclude, do we have questions about the U-statistics as a whole topic? Because my plan is that in the next lecture, I want to start a new topic to talk about Bootstrap. So maybe I can just ask people, do you feel like compared to previous parts, do you think this part is easier to understand or more difficult to understand or similar? So if you found this more difficult, maybe you can raise your hand so I can see. So actually I have one. Okay. Yeah, actually I think this is normal because I think by nature, the statistical functional interpretation is actually more abstract. So that's why I feel like examples like this variance, right? Unbiased sample variance. Yeah, I have another hand, thank you. Yeah, so this will actually help you make the abstract concept more concrete by associating them with what we know. But this is what mathematical statistics try to do, try to generalize things. Okay, so if there are no more questions, my suggestion is that if you have time, right, when you have time, because we don't have much homework left for you, so just try to read the notes. I think that will help you understand the contents better. So if there are no more questions, I think we can stop here. And so I will see you in the class next Monday when we start a new topic. So thank you and see you on next Monday.